All right, let's get started. I just want to tell you that we more or less finished grading and we'll release the grades today. You can pick up the homework, the graded exams tomorrow by coming to my office or setting up some appointment with one of the TAs. And I'll also bring them on Friday to the lecture, okay? Sounds good? Okay, all right, so let's continue with the discussion about maximum flow. Just to recap, what is a flow, right? You know, a flow can be thought of in two ways, but we'll work with the edge-based flow right now. So I have a network, a graph, a directed graph where every edge has some non-negative capacity. And I have two words is S and T, and I want to send as much flow as possible from S to T. What's a flow? A flow is a function, if you think about it in edges, a function which assigns to each edge a number, how much flow is going on that edge, right? And what should it satisfy? To be a flow, it should satisfy a flow conservation. That means that except at the source and the sink, the incoming flow should be equal to the outgoing flow, right? So the sum of all the flows coming into a vertex should be equal to the sum of all the flows going out of the vertex. That's flow conservation. And for every edge, the flow on the edge should be at most its capacity. So those two properties are the properties of flow. And subject to this, what is the value of the flow? The value of the flow is how much is leaving the source, right? Which is the same as how much is entering the sink. And the maximum flow problem is find me a flow of maximum value in a given graph. Okay? That makes sense? Yeah? Okay. And what is a simple greedy algorithm for trying to find a flow? We just look at the graph and you say, okay, how do I send any non-zero amount of flow? How can I find some flow? Well, then it's better to switch to the path-based view of flow and say, okay, I'll find a path from S to T and send, which has such that on the path, every edge has at least positive capacity, right? Has positive capacity, and say, okay, if I find one path, I can send some flow on that path, right? By putting some value on that. How much can I put on that path? The minimum capacity of any edge on that path, right? So for example, here is a graph and I can find some path. That's easy to find a path from S to T, and I can throw away zero capacity edges because they're not useful to me, right? So in this graph, you know, I could send 10 units on this path, right? I just find any path and say, if I find a path, how much can I send? Okay, I can send 10 units because the minimum capacity edge on this is 10, right? So I put 10. Okay, now I've used up some capacity on those edges, right? All right. So I take out that capacity and then say, okay, I find another path and keep adding greedily. Okay, that's a simple greedy algorithm. And as we saw an example where basically the greedy example doesn't work to give the maximum flow, right? Because you could choose a wrong path and get stuck on a wrong path, right? So you should, I mean, it doesn't work to always. It works in some examples, like many heuristics, but in general, it won't give you a maximum flow. Okay, so why doesn't it give you maximum flow? The intuition is that, well, you know, you made a mistake in the original first path by maybe that's not the right way to send flow on that path, and you may think, okay, maybe I can find a clever path. But its question is, how do you find such a clever path so that in the first iteration you make the decision and you never make a mistake after that, right? So that's a hard problem, so we don't know how to do that. So instead, what we can do is we find a path, send some flow, okay, we made some progress. But if that is a mistake, then we should have some flexibility in correcting that mistake, right? Well, it's not obvious what that would be, but one way to do it is to use the notion of a residual graph, the ability to change or reduce flow on an existing path, right? You know, you send some flow on an edge and say, okay, I don't want that. How do I take out that flow locally? So to give ourselves that flexibility, we defined the notion of a residual graph. And so what is the definition? Let me go over it because it's very important for what follows. You start with the graph and you already send some flow on the graph, right? So we already have a flow, right? Some numbers on the edges, right? and the residual network is defined with respect to the original network and existing flow. Okay, and how do we do that? We look at each edge of the current graph. What do we have? Two numbers. One number is the capacity of that edge. The other number is how much flow we are currently sending on that edge. Right? So what do you want to capture? If I am sending 10 units on an edge of capacity 25, I want to feel that, okay, I can send 15 more units in the same edge, right? I have capacity, spare capacity of 15 on the edge, if I want to use it in that direction. So for every edge, we retain that edge if there is spare capacity. Okay, what is non-negative spare capacity? If it is 0, if it is already full, then we don't have any spare capacity, so we don't put that edge. Okay? If there is spare capacity, we put an edge in that same direction and put the capacity of that edge as whatever is left. Okay? CE minus the current flow FE. That's the forward edge. Okay, we also want to have the ability to reduce flow, right? So but we don't want to use negative numbers, so we simulate that by saying, aha, okay, if I have a flow of 10 units on this arc, how much can I reduce flow on that arc without going below 0? 10 units, right? So I put an arc in the opposite direction with capacity 10, with the understanding that if I send flow on that edge, I'm actually reducing flow on the original edge, right? So that's why we effectively for each edge we create two new edges, one in the original direction, the one in the negative, the opposite direction, and the capacities are set appropriately. Okay, so that is the notion of a residual graph, and here is an example. See, currently we have this network where the black numbers are the capacities and the red numbers are the current flow. Remember, we sent 20 units along this path, and and if you recall this algorithm, this is not the right thing to do. So we need to have the ability to change that flow. So what do? On this edge, there is no spare capacity left to increase it, right? So we don't put an edge in the forward direction because there is no capacity left. But on the negative, in the opposite direction, we put 20 because we can reduce the flow by 20. And what about this edge? On this edge, the spare capacity left in the forward direction is 10, so we keep a 10 capacity edge in this direction. In the opposite direction, we keep a capacity 20 edge. Okay? So for every edge, we do this. Okay? That is the definition of the residual network. Okay? Okay? So we denote it by G subscript F because it is a function of both the original graph and the flow. Right? It depends on both. So we call it GF, and it's called the residual graph. And okay. In some sense, not some sense, we can formally prove the following, that once you have a flow, the residual graph completely captures what you need to do. Okay? So we need to prove two lemmas to do that, and these are the two lemmas. Let me go over them. We didn't go over them last lecture. Suppose I have a flow in a graph and GF is a residual graph. Okay? Now I forget about the original graph and I work with the residual graph. Okay? I have a new graph, right? Suppose I send some flow on that in the residual graph. Let's call that F prime. Okay? The claim is that you can take that F prime and add it to the original flow F in the original network and get a new flow in the original network. And how much value is it? The value of the original flow plus the value of the residual, the flow F prime you sent in the graph GF. Okay? So what is it saying? That if somehow you solve the problem in the residual network optimally or however you want and get a flow of F prime, a flow and F prime, you can take that flow, add it to the original flow and get a new flow. Okay? So that's good, right? That means that you can solve the problem in the residual network and add it to the thing, right? Okay? That's one property you need. The other property which is very important is that you have to ask yourself the following question, right? Suppose I sent some flow and I didn't know how I sent it in some arbitrary way. Can I go from my current point, that means my current solution, always to the optimum solution? That is, am I stuck with if I compute a bad flow currently, so F is not the right flow in some sense, right? Can I always move towards the optimum solution? Right? That's important too, right? Maybe if there is nothing you can do because I already got stuck with a bad flow. That's not a good thing, right? So what we can show is that No, you're not stuck. In some sense, the residual graph captures everything that you can do. What it says is that if you're at a flow F, and suppose it's a new flow, I mean, in fact, there is another flow which is actually bigger flow than current flow. So let's think of this as the optimum flow, right? Which is the maximum flow. Okay? And the value of the flow is bigger than the current flow. In fact, it's more interesting if you put greater than. But then what it says is that you can send V of F prime minus V of F in the residual network GF. Okay. What it is saying is that, if there exists a bigger flow than your current flow, then you can work with the residual network and send the difference of the flows in the residual network. Okay. So combining these two lemmas, what do we get? Okay. If you had these two lemmas, this is what you can do. I have a current flow. Maybe it's not maximum, right? If it is not maximum, what can I say? From the second lemma, I know that if I look at the residual network, the amount of flow I can send in the residual network is the difference between the maximum flow and my current flow. Right? That's what the second lemma is saying, right? You look at the residual network, if my original flow is not a maximum flow, then there's a bigger flow I can get to. And in fact, indeed, if you look at the residual network, you can send the difference between the maximum flow and my current flow in that residual network. And then this first lemma says, you can take that flow and add it to your current flow and get the right flow in your original network. So you can recursively reduce it to the residual network, right? With these two properties, basically, you can always get to a maximum flow by this recursive algorithm. What is this recursive algorithm? Okay, I didn't define this plus and minus because these are vectors, right? Flows are vectors, they are not numbers. Okay, so what is the definition of plus and minus? It's very intuitive from the definition, but I won't go through it right now because it's a bit painful. But we'll see a special case of this and you will prove this in the homework. Okay, so I won't do it right now, but assuming the lemmas are true, this I claim is a algorithm to find the maximum flow. So what do? You start with the graph. If the flow from S to 2 is 0, then return 0. Can we check whether the flow from S to 2 is 0? When is the flow from S to 2 is 0? There is no path from S to T which has non-negative capacity. Right? That's the only reason why the flow from S to T is 0, right? If there's any path from S to T with non-negative capacity, you can send some unit or some flow on it, right? Yes? So this is easy to check. So this is the base case, right? There's no flow. Okay, then we can check. Then you return 0. Okay, nothing to do. Otherwise, you find any flow on the graph G. Okay? Okay, I'm not saying how, but how can, yeah.
So I'm not totally clear on this. Like the G that we're being passed in right now, that has capacity, but in addition, it also has flows assigned to you?
No, it doesn't. No. It is just a G, right, an S and T. And this is an algorithm to compute a maximum flow from S to T in that graph. So this doesn't have any flow on it. Okay, it just has a graph. And the problem here is, the input to a max flow problem is a graph with capacities, the source and the sink. That's it, right? We want to compute a maximum flow. Okay? So if the flow from S to T is 0, then we can find it, right? That means we can say done, there's no flow. Okay. Otherwise, find some flow. Why is this easy? Can you find some non-zero flow? Yes, right? You find a path and just send some flow on it, right? It's easy to do, right? But maybe you can find other ways of sending a flow, right? But at least you can find some non-zero flow if it exists, right? Okay. Do that, and then what do? You compute the residual network GF. Okay, and recurse on that. Okay, you recurse on that, and what does the recursion do? It will give me a solution, an optimum solution to the flow problem in a new network, right? Why is it recursion? Have you made any progress? Sorry? Yeah, we found some non-zero flow, right? So the optimum flow in the new network should be a little less than the original flow, right? Okay. Okay. So in some sense, we are not making the graph smaller. All we know is that the value of the flow in the new network has to be a little bit smaller because we already sent some flow in the original network because of the two lemmas we have. Okay?
The value has to be smaller.
In the residual network. If the value is bigger than the original network, then that will prove that I have a bigger flow than what I thought in the original network, right? Okay, so this is a small point you have to think a little later, but okay. So and what do we know? If we find a flow in the residual network, we can add it to our original flow, right? And get a new flow. So if you had these two lemmas, you can convince yourself that this would give you an algorithm which will eventually converge to the optimum solution. Okay? Now the issue with this algorithm is that you don't know how long it will take to converge, right? It's sort of, this is one of those things where we are getting into the point where it is not so obvious, the termination is not obvious in this kind of algorithm. Even though you know that this will eventually converge to the optimum algorithm, the running time is not obvious. Because we had all these statements like, for example, we don't even know if the value of the flow is going to be a rational number or an irrational number. Okay? So it's not obvious that this will actually converge. Okay? So that's but we do know that this algorithm will eventually in the limit converge to the optimum flow because of these two lemmas. Okay? So in a way this is a high level algorithm. Okay, now we can take out the recursion. The recursion is very simple. Instead of recursion, you can think of a iterative algorithm, which is just the same algorithm but is slightly different. You start with a flow that is 0 on all the edges. So that's a feasible flow, right? That's a basic thing. And now what is the residual graph of the original graph? It's the same graph, right? Okay, then you try and find any flow, find some flow in this graph. Now, and you add it to your, so your original flow is 0, you find a flow f prime in the residual graph of non-zero value and you add it to your current flow and update the residual graph. Okay? This is the same as this algorithm, we removed the recursion and made it iterative. Okay? Does that make sense? You start with the flow, okay? We say, okay, is it a maximum flow? If it is a maximum flow, we stop. Right? Somehow we have to detect it's a maximum flow. Let's suppose we somehow knew that. If not, what do? You compute the residual network, okay, and find some non-zero flow on that residual network. If you find any non-zero flow on the residual network, you can add it to your original flow and increase your flow, right? And you do that and recompute the residual network and keep doing it. Yeah? That makes sense? Okay. All right. So, what is the simplest way to find a flow in a network, non-zero flow? As we talked, you find a path with non-zero capacity, right? That's the simplest way to find some non-zero flow, right? Okay? That makes sense? Okay, and that's the Ford-Fulkerson algorithm. What is it? You don't think about it in this abstract thing, you simply say, at each step, how do I increase the flow? Find a single path which has all capacities at least positive and try to increase flow on that path. Okay? And that's it. This Ford-Fulkerson algorithm is initially set all the flows to be 0. You compute the residual network and you want to find a non-zero flow in the residual network. What does it mean, non-zero flow in the residual network? Okay, how can I find a non-zero flow? I only know one simple way of finding a non-zero flow, a path from S to T. Okay, so if there is a path from S to T, augment along that. That means that you send flow along that. Okay, okay, now we have to add that flow to the original flow, right? So that process is called augmentation of the original flow. Okay, we'll see the details of that, and then you get a new residual graph and you repeat. Till what happens? At some point, you cannot find any flow on the residual network, and then you stop. Okay, now the question is, will you ever get to that point? We will come to that, right? Maybe you will keep on doing, and the amount of flow you add keeps on getting smaller and smaller and smaller and smaller and smaller, and maybe it's like, 1 plus half plus 1/4 plus 1/8 plus, you'll never terminate, even though you know it's converging, right? Alright, that may happen, right? With this algorithm, you don't know whether that may happen, right? So we have to argue that it won't happen and you'll terminate and stuff like that, okay? Okay. Okay, so now let me give an example and then come back to because it's much easier to see it in an example than okay. Okay, so what is this? This is the network, right? Okay. Let me see how I want to do this. I have a lot of what is the residual network? So initially, what is the flow? The flow is 0, 0, 0, 0, 0, right? What is the residual network of this flow? Same thing, right? Okay, let me draw the thing just to be very rigorous. Okay. Okay, the capacities are how much? Okay, the same as the original capacities, right? Okay, now I want to find some non-zero flow on this, and the only way I can find non-zero flow, the simplest thing is find a path. Okay, find any path. Give me a path. What do you like? Okay, let me see. Okay, S what? Okay, I take this path. Okay, how much can I send on that path? Check 10, 15, right? No, 15, right? Okay, I want to be greedy because it'll help me, right? And I just say 15, right? Okay, I can send 15 units of flow on that, right? Okay, if I send 15 units of flow, what do I get? What is the new flow I get in the original graph? 15 on this edge and 15 on this edge, right? So I put 15 here and 15 here. That's my new flow, right? Of what value is it? 15, right? Okay, what is the residual network of this? Okay, so let's draw the residual network. This is still 10, right? That won't change, right? I'm computing with respect to this, right? This flow and okay. This is 30, right? This becomes 15, right? Okay, and this stays 10, and okay, then this you get 2 arcs now, right? Right? How much do you get? 5 and 15, right? Okay. Now you say, okay, I want to send some non-zero flow on this network. Okay? Okay, give me a path in that network. Sorry? SUT? Yeah? Or you want to make it more messy? Okay, SUT. It doesn't matter, right? Okay, how much can I send on that? 10 units. Okay. Now we'll get some, okay, we send 10 units. Now we need to add this 10 units along this thing to my existing flow. This is the addition thing, right? Okay, what is the natural thing? I mean, in this case, the edges are not overlapping. So it's not hard to convince yourself that the new flow will be 10, 10. This doesn't change, right? We didn't touch this path. Okay, no, what is this? 15 and 15, right? You agree that this is the new flow you'll get? Yeah? Make sense? Okay, now we compute the residual graph of this. What is that? Okay, now this becomes 10, right? Now we get 2 arcs here, 10 and 20. We still have 10 here. We again get 15. How much? Okay, 5 and 15. Okay, okay, we keep doing it. Okay, we have to find another flow on this residual network now, right? So before I run out of colors, right? Okay, let's find a flow, a path. Give me a path. There's only, right? Is there any path? You're stuck? Yeah? Yeah? Are we stuck? Yeah, it looks like we're stuck, right? Are we stuck? Yeah. Okay. So, is that a maximum flow? How much did we send? 0. Sorry, no, not send. I mean, now if you're stuck, right? You must be optimal, right? If you believe the lemma, you must be optimal, right? Yeah? Because if you are not optimal, there must be some flow in the residual network, and we know there is no flow in the residual network. Okay. Okay. How much flow are we sending? You know, 25, right? Okay, is there a way for us to convince ourselves that that is correct? Why is that correct? Sorry? Is there a cut of value 25 just to convince ourselves? There must be if the Maxflow mincut theorem is true, right? Yeah? There is a cut. Can you see the cut? Yeah? This edge and this edge, if you remove, you can't go from S to T, no? And the capacity is 25, right? So it is optimal in another proof, right, that it's optimal. Okay? Okay? So is the algorithm clear? Yeah? Alright? We didn't have to choose the single path. We could have chosen any flow, right? Except that finding a non-zero flow, the easiest thing you can do is find a path. Yeah? Okay? Alright? Okay. Now I want to convince you of two facts. One is that this addition makes sense at least in the restricted setting that you have a single path on which you're increasing flow. Okay? So I just want you to think about the following picture, right? The following picture that when we went from, take this network, right? When we routed this, okay, so I want to do something. I'm going to erase this and I'm going to take let me see. Can I redo the example so that to illustrate a point? I want to redo the example by choosing a wrong path. Okay? Alright? To illustrate an example. Okay? Let's see. Okay, I have enough pictures. Okay. Okay. So suppose, you know, in the first iteration, I didn't do the right thing. Okay? And I did the following. So remember, this is I'm going to restart the algorithm, okay, from scratch. So initially I have 0, 0. So what is the residual network is the same as as this, right? 15, 30, 10, 10, 20. Okay. Suppose I chose the wrong path, whatever the wrong means here, that I chose this as my first path in the residual network. Okay, what happens? Well, then, you know, I get a flow of value 10 here, 10 here, and 10 here, right? Okay, then what is the residual network of this? You get this 10, 10, 20, 5, 10, 30, right? Make sense? Okay, now I have to find a path in this. What would be a path in this? Okay, let me do an example to illustrate. So suppose I can do this now, right? Just to right, I'm choosing this path. Okay. Okay, what happens when I do that? Okay, what is the new flow I get in the original graph? So I have to, basically what I need to do, my current, this is my original flow, right? This is the residual graph, okay? And I send 10 units on this path now. Or you could really think of it as a flow of 10 units on that residual network. I want to add that flow to my original flow. Okay, what does it mean to add, right? Okay, let's look at this edge. What is the flow on this residual graph? 0 on that edge, right? So we will still get 10, right? Okay, what about this guy? It was 0 here, right? We didn't send any flow here, but here how much did we send? 10, right? So we should get 10 here, right? Okay, what about this arc? This was 0 here, but now we get 10, so it makes sense that we get 10, right? Okay. What about this arc? It had 10 here, But here it has minus 10 because you're going the opposite direction. So it should cancel out and you should get 0. Okay? Okay? And then what else happens, right? This guy still has 10. Yeah? That makes sense? Okay. Now what is the value of the flow in this? This is 10 here, now it is 20, right?
Wait, does it have 10?
Sorry? Yeah, see, remember it had 10 here and here we didn't do anything to it.
Oh, so the 5 going to the T that...
We didn't send any flow on that, no?
Oh, right.
We didn't, 0, 0 on both of those. So how do you add 0, 0 on both of this? We didn't do anything to that arc. Okay, does it make sense what we're doing? Okay, yeah? So took this, so what this is saying is that you can take the flow on the residual network and it makes sense to add it to the original flow and get a new flow of the right value, right? Okay. This example, right? Okay. Okay, yeah, question.
In the second iteration, what if you choose SVT?
I could have chosen any path. Okay, I mean, I have freedom to choose any path I want. The point of this thing is that I don't have to be clever of about choosing the path, because whatever you choose, you are going to improve.
So choosing every path will converge optimally.
No, so that's the point, right? It increases the flow, right? Because if you choose a path here in the residual network, if we find a path, it has to have non-zero flow, right? I mean, we remove all the zero capacity edges. There are no zero capacity edges, right? So any path should increase a little bit of the flow, right? It may be a very tiny amount, right? But the new flow will have at least that tiny amount added to the original flow. So we get a better flow, right? Okay, now the questioning is, yes, you get a little better flow, but what if it is very tiny, and how many times do you have to do this before you get to optimal flow? Okay, it's not even clear that this will give you the right maximum flow without those lemmas which one has to prove, right? What does the lemma say? That if you are not optimum, you can actually always find a non-zero flow in the residual network, right? That lemma says that, which we didn't prove, right? Okay? Okay, I'm not going to prove that lemma because you're going to prove it in the homework. There is a different way of proving the correctness of this algorithm using cuts. You'll get a new nice Maxflow mincut theorem as a consequence. Okay? So there are two ways of thinking why this algorithm converges. One is just this convexity of this flow, which we'll see the intuition for later on. The other is because of this nice duality between flow and cuts. Okay? Okay, but I'm just giving you the algorithm. Does the algorithm make sense? Okay. Now, how do we prove that this is correct, right? Or that it makes sense? Okay. So the claim is that if f is a flow, if I have a flow, and I found a path in the residual network with non-zero amount of flow, right? We'll assume that all edges are right. Then the notion of augmenting makes sense. What is the notion of augmenting? Well, here is the augmentation. The algorithm is the following, right? Formally, you know what we did, right? What does the augmentation mean? That is, this is the current flow. Sorry, let me take this example. This is the current flow, and I found a path in the residual network. What does it mean to add that flow to this flow? You look at each path in each edge in the new path you found, go back to the original flow, and do what? If they are in the same direction, you add the numbers, okay? Okay, so here, this edge is 20, and it had 0 here, so we add 20 and 0, sorry, this flow is 10 units, right? This blue flow is 10 units. We add 10 to the flow on the original flow, but the original flow is 0, so we added 10 here. That's a new flow on this edge. What about this edge? We are sending it it's a reverse arc, right? So if you send 10 units on the reverse arc, you should go to the original flow and subtract. So we subtracted, we got 0 on this, right? So it had 10, and when we did this, we got 0 here, right? Okay, what about this edge? We had 10 units on this thing, and it had 0 here, so we added and we got 10. That's the code, the formal, that's the definition of taking the path in the augmenting the residual network and adding that flow to the original flow. Okay, now I want to claim that the new flow, what you get is actually a flow. Okay, so what do I need to prove if I want to prove that it's actually a flow? These new numbers, are you convinced that it's a flow? So what do you need to prove to convince yourself that this is a flow? These numbers actually define a new flow. First you have to prove that the capacity constraints are not violated, and two, you have to prove that the flow conservation is satisfied, right? Okay, is it intuitive at least that that is true? Yeah, from the pictures it should be kind of intuitive, right? Okay, why is the capacity constraint satisfied? Okay, but that's how we set up the residual network, right? What did we put? What numbers did we put on this, right? On the why did we put 0 in this direction? Because there is no capacity left to increase, right? Okay. So let me go down to this. So I want you to understand the statement of what we are trying to prove. Okay. What we are trying to say is that if you start with F and look at the residual network and you send some flow along a path, this process of adding that flow to the original flow creates a new flow is a lemma. It is saying that it is actually you get a new flow, right? Okay. To verify that, it's very intuitive. It is not there is nothing complicated about this. It's just that being rigorous about this, right? You need to verify that in fact F prime, these numbers are actually a flow, right? So how much flow did we send on that path? How much flow did we send? Well, the maximum we could send, right? What is the maximum is the B, which is the bottleneck, right? We couldn't send any more than that B because some edge would not have more than that capacity, right? So B is so in this example, the B was why did we send 10 units on this, right? Why did we send 10 units on this? Because that's the maximum we could send on that, right? Okay, so that's called the bottleneck capacity because that's the maximum you can send. So okay, we send B. Okay, we have to verify capacity constraints, right? That means for every edge we have to prove that F prime of E is less than or equal to the capacity of E. Okay, how do you check that? There are two cases. Suppose the edge on the path is UV, right? Some edge, right? Pick any edge. One is that if that edge is a forward edge, what can we say? What does it mean it's a forward edge? That means that it's an edge which had some flow in the original graph but had some extra capacity left, right? But what if we put the capacity of that edge in the residual network? Only how much ever their extra capacity is, right? And B is less than that capacity, right? Because we chose B to be not more than any capacity. So we could not have sent more than the capacity available on that edge. B plus what was there previously cannot exceed the original capacity of the edge, right? That's how we set up the network. Okay? Yeah? Okay, so that is one case. What is the second case? The second case is that the edge that is on the path is actually a reverse edge. Okay? If it is a reverse edge, what happens to the flow in the original graph? We subtract how much we sent on that edge from the original flow, right? What is the danger in this case? We are only subtracting, it means that we may go below 0, right? We don't want to go below 0. That doesn't make sense, right? Flow should be non-negative. Okay, but how much capacity did we put on that reverse arc, right? The amount we had in the, so we cannot send more than the original flow on that reverse arc. So even if you send as much as the original flow, we would still get only 0. That's precisely why we did not put more capacity on that, right? We don't want to go below 0. Okay? So this proves that the new numbers you get are actually satisfy capacity constraints. They are non-negative and that makes sense, right? That's how we set up the residual network. Okay, the thing you need to verify, which is the more tricky part, is not tricky, it's very intuitive, it's a flow conservation. Okay? That for every vertex, after we do this addition and subtraction of numbers along that path, that flow conservation is satisfied. But it's very intuitive, right? Why is it true? Forget about the fact that they're positive or negative, right? We had some numbers which satisfied flow conservation, right? And we found another path, right? And we then kind of added those numbers. It doesn't matter whether they're positive or negative. But this flow had satisfied flow conservation. The path obviously satisfies flow conservation, right, at every intermediate vertex. Whatever is coming in is going out. So if you take two things that satisfy flow conservation and add them up, it should satisfy flow conservation. Okay, because the incoming is outgoing, right? I take two sets of numbers which satisfy incoming is going outgoing, and I just put them together. It should satisfy it, right? I didn't do anything interesting. It's just like adding numbers, right? Okay, that's not a proof, but intuitively it is not difficult proof, right? You shouldn't be surprised. It is actually very easy. Okay, if you want a formal proof, sometimes intuition can mislead us, right? So sometimes you have to sit down and say, do I really believe it? Maybe it's not as intuitive to me, right? And so you have to say, okay, how do I convince myself? Okay, if you want to convince yourself, look at this picture, right? So what it says is that, so look, we had a graph G and we had a flow on it, right? And then what we found? We found a path in the residual network. Okay, and some of those edges are black, some of them are red. What does this black mean? That this is a forward edge. Red means that it's a reverse edge, right? I don't know. It could be any kind of combination of those things, right? Okay, so if what do we do in the residual graph? We put positive numbers on all these edges, right? Okay, but when we come to the original network, what do? If this is plus, we get plus. We get plus. We get plus, but since this is a reverse arc, in the original network the arc is going this way and we are subtracting, right? That's what is happening, right? Okay, now you can see easily that the only vertices where flow conservation can be affected is the vertices of this path, right? Okay, so now you can go and check every case. Okay, a vertex can have one forward edge coming, one reverse edge coming, one back, if there are some 4 cases, right? But that's not the right proof. Okay, the right proof is you take two flows which satisfy flow conservation, you put them together, don't worry about plus sign, minus sign, okay, then they should satisfy flow conservation. That's a better way of thinking about this. This is just in case, sometimes we get a little worried and we want to try all possibilities and just convince ourselves. This is that proof, okay, alright, but don't worry, that your intuition is right? We take a flow, we add a flow. If you don't worry about the capacity constraints, it's very easy. And we've already ensured that the capacity constraints are okay, and that's the reason why we set up the capacities in the residual network the way we did. Okay? Alright? At least intuition is correct. Okay. So that's the thing, right? Okay. Now it makes sense, right? Now we want to argue the following. How do you prove termination, right? That's a tricky part in this proof, right? Maybe we'll. So here is a simple observation that if we suppose all the capacities are integer valued, okay? Let's assume they're all integer valued. The algorithm had the following simple property that if you start with an integer flow, you stay an integer flow. Why is that?
Because at every point you're going to choose a path and choose the maximum edge on that path.
Right. What are we doing? We start with an integer flow and the capacities are integer, right? Yeah? Remember, suppose we have an integer flow. Initially the flow is integer value, right? Because you're starting with 0. That's true, right? And all the capacities are integer. At any stage, what happens? We have an integer flow. What happens to the residual network? What are the capacities in the residual network? They must be integers, right? Yeah? Because they are just the subtraction of the capacity minus the current flow, right? Or the current flow, right? What are the capacities in the residual network? There are two possibilities for the capacity. Either it is the original the current flow in the negative direction, or capacity minus flow, right? Okay. So if you have integer flows and integer capacities, your residual network will also have integer capacities. Is that clear? Yeah? Okay. And how much flow do we send on the augmenting path? It is the minimum capacity along the path, right? So that is also an integer, right? Because all the capacities are integer. And then we take out that or add that quantity to the numbers, right? So we are only adding integers at any point, right? So everything will stay integer if we keep going, right? Yeah? Because of the choice of the how much we are sending is exactly the minimum capacity along that edge. Yes? It's clear that we have integer capacities? Okay. If you have integer capacities, then what can we say? We can say that the value of the flow is increasing, right? At each step we are sending some flow, right? How much can it increase by? The minimum is at least 1 unit, right? If all the integer capacities, right? Okay. So we start with 0 flow, and each step, if the capacities are integer, we can increase the flow at least by 1 unit. Yeah.
Yeah, I thought the lemma said that it could be greater than equal to.
Sorry?
I thought the lemma said that we could also find a path with which retains the capacity, doesn't increase it.
No, the capacity, the flow value has to increase, right?
Okay. I thought the lemma.
Which lemma?
That was like what you said.
Or the original lemma? Okay. Oh, this one?
Yes.
Okay. Which this one?
No, the second.
Yeah. But if this is non-negative, then okay. If this is strictly bigger than that, okay. So what is it saying, right? If you have a current flow, if there is a bigger flow in the new network, then the amount of flow you can send is this much, no?
But so there can also be a flow of the same. That's the same, right?
No. But this is the amount you send in the residual network is the difference,
I see.
right? If they're the same, right? If you're not a maximum flow, and there's a bigger flow, how much flow can you send in the residual network? The difference, right? So suppose my current flow is 10 units and the maximum flow is 30 units. What this lemma is saying that you can send 20 units in the residual network, right? Okay. If you send what is the first lemma saying? That if you send any flow in the residual network, you can add that flow and get the right value, increased flow in the original network. So okay, so this is what I am trying to claim. The lemma says that if you have a flow F and you found a non-zero flow in the residual network, you increase your flow in the original flow network, right? You add them up, right? So in each iteration, if you don't stop, in each iteration you are adding at least 1 unit of flow, right? I mean, adding 1 unit of flow means that your flow value is increasing by at least 1 unit. Yes? After augmentation, right? Is that clear? Yeah? No, this is not clear? I see some worried faces, right? See, the point is that if you start with integer flow, we stay in integer flow, right? Is that clear? Yeah? Okay. If you don't terminate in each iteration, we must be finding a path in the residual network and sending some non-zero amount of flow, right? Because if there is no path, we'll stop the algorithm because we are stuck and we don't have anything to do, right? We are done, right? So in each iteration, either we stop because there is no path from S to T in the residual network, or we find a path and we send at least some integer amount of flow on that, right? What is the smallest integer which is not 0? 1, right? So we'll find at least a path of capacity 1, and then we add that flow to the original flow. When we add that, we increase the flow, right, by 1 unit. Okay? So maybe we are going very slow, right? And so what happens? If how long can we continue this process? It depends on the maximum flow we can ever send in the network, right? Yeah? Do you have an upper bound on the amount of maximum flow we can send in the network? Yes, we do, right? If the maximum capacity of an edge is C, we cannot send more than M times C in the network, right? Why? Because that's a cut. If you throw out all the edges, clearly there is no path from S to T, so we cannot send more than M times C in the network. Yeah? Where C is the maximum capacity, right? That's the maximum flow you can ever send in the network, right? So if you send only 1 unit per iterations, still doesn't matter. In M times C time, you will be done, right? Yeah? Yeah? Okay. So you will terminate, right? Yeah? Okay. Agreed, you will terminate? Okay. If you had the lemma, this proves to you that it's actually a maximum flow, right? Why? Why does it prove to you that it's a maximum flow? So this proves termination of the algorithm, right? Okay, but the lemma says that if you terminate, then you're right. Yeah? Yeah? Why does it say that? Because if you're not a maximum flow, it means in the residual network you must have some non-zero flow. But there is no non-zero flow, otherwise you'd keep going, right? But because we are maintaining only integer flows, we can prove termination. Okay? As a byproduct, what do we get? We get the very nice property that for every network, if the capacities are integers, there is a maximum flow which is integer valued. This is a very important property, right? It is not obvious at all, right? From the definition, it is not obvious that the maximum flow has to be integer valued. Is it clear? Even if the capacities are integer, it is not guaranteed that it should be integer valued. Okay? Right? You get this extra property for free. Okay? But maybe you don't, I didn't prove the lemma to you, so you shouldn't trust me, right? You know. Okay? So I'll prove it to you in a different way, which gives us the Maxflow mincut theorem as a very nice byproduct. Okay? Okay. So what do I want to prove? I want to prove that, okay, first before I go to prove that, you might say this is a very slow algorithm, right? Why? Because here is an example. Take this network, right? Okay, this should be, okay, C is huge, C is 10 to the 50, okay, okay. This is a very small network, but C can be very large, right? What is the optimum flow in this? 2C, right? Yeah? Why? Because you can send C here and C here, okay? Okay, but suppose I didn't know, I was like a crazy guy and I'm finding the paths in a bad way, right? You know, I was not paying attention, so what will I find? Suppose I find this path first, okay? How much can I send on that? 1 unit, right? Okay, but then what happens in the residual network? What do I get? What is the residual network if I send 1 unit on that? Okay, maybe I have a picture. Okay, I have a picture. Okay, the residual network is this, right? You know, I didn't put directions on this. Okay, in the residual network, I know I can be dumb and I can send it again like this, 1 unit, right? But then what happens? You will get back this graph. The residual network after that will be, you will get 1 unit like this, 1 unit like this, and I can find again this silly path. So I can force, if you are not clever about choosing the path, you can go slowly 1 unit, 1 unit, 1 unit, 1 unit. It will take how long? 2C units, right? Because the flow is 2C, and in each iteration you are only adding 1 unit of flow. Okay? Agreed? Yeah, so the algorithm can take a very long time to terminate if you don't choose the paths carefully, right? But it will terminate, yeah? Agreed? Okay, now let me prove to you that this algorithm is optimal. You know, we already understand that if it terminates, it's optimal from the lemma, right? But the lemma is something that I haven't shown you. So I will give a different proof, and which gives a nice consequence. What I'll show is that at the end of the algorithm, I'll give you a cut such that the capacity of your cut is equal to the flow you found. If I prove that, then you're done, right? Why are you done? Because I know that, you know, I can't be more than the cut ever, and I reached the cut, right? So, that's great, because that also proves that my maximum flow is equal to the minimum cut. It has to be a minimum cut, right? I can never exceed the minimum cut, and I'm going to give you a flow that is equal to the value of a particular cut. So that must be a minimum cut, right? Right? So let's see why that works. Okay, everybody remembers the cut, I assume. So here is a, I mean, I'll give you a proof, okay, by picture, okay? So let's see. So I start with this flow, okay? I mean, I have a flow. This is a flow, okay? This is took me a while to draw these pictures a few years ago, right? So this is a flow, and it's integer valued, right? You know, and why did I stop my augmenting path algorithm here? Well, because I computed the residual network, right? This is a residual network of this, okay? So you look at this 10, 20, it should be 10, 10, 5, 5, and okay. Okay. So what happened? I tried to send flow from S to T in this graph, but I couldn't, right? What does it mean? There is no path from S to T in this graph. Yeah? Agreed? Yeah? Is there a path from S to T in this graph? Okay. How do I check that, by the way? How do I find whether there is a path from S to T? Aha, okay, now you remember. Okay. Okay, but if you know, what does the DFS return to you at the end of it? You know, how do you know whether T is reachable or not? So so the algorithm, it goes, figures out something and says, I reached all these guys and I couldn't go any further and T is not in that set. Okay? So the algorithm actually finds everything that S can reach, right? Okay, in this graph, what are the things that S can reach in the residual network? Okay? Okay, I drew it here. These are all the vertices that S can reach. This circle, let's call that set A. Right? So S can reach this vertex, right? Yeah? S can reach this vertex? Yeah? Because there's a thing, right? Can S reach anything else in this network? It cannot. What does it mean that it cannot reach any other node? What should be the property of this A?
Strongly connected.
No, it's not. Doesn't have to be strongly connected.
Connected.
S should be able to reach this set A, but why can't it go outside that set? There cannot be any edge that is leaving the set A, right? If there is another edge leaving the set A, I'll go out, right? That also is reachable from S, okay? It means all the edges are going into this thing, right? Yeah? Agreed? Yeah? But this is on the residual network, right? Agreed? I couldn't reach T in this residual network, okay? So I got stuck. So I look and say, this set A is the only thing S can reach in the residual network. Let's go back to the original network now. Okay? Remember, this is not the original network, right? This is the original network. This is for a fixed flow which we found the residual network, and we tried to increase flow. What does it mean try to increase flow? We tried to find at least one path from S to T and we failed. Right? So we got stuck, which means that we look at this set A that S can reach, and we said, we can't go out of this set A anymore. Right? Agreed? Okay, so that means all these arcs are coming into this, right? Okay, then we say, okay, why is this arc coming in here? Okay, so we go back and say, this is it a forward edge or a reverse edge? Okay, this turns out that this is a reverse edge, right? So why did we have a reverse edge here? It means that the flow on this edge must be exactly equal to its capacity, no? If it was a reverse edge and we did not have this edge, it means that edge in the original graph is saturated. What do you mean saturated? The flow is equal to the capacity. Right? Agreed? Okay. Okay, so that is that. Okay. Okay, but what about this edge? This edge is actually a forward edge, right? Okay, let's look at it in the original graph. Why did we not put a reverse edge in the residual network? Because the flow on that is 0. Right? Agreed? We are looking at the same set of vertices in the original graph and in the residual network, but the arcs are not the same, right? Okay, the arcs are different. Why did we have no arc in this direction, even though that's because this edge was saturated? Well, this edge, which was, we have the same edge here, okay, but why did we not put a reverse edge in the thing? Because the flow on this is 0. Okay? Okay. So from that, what can we conclude? What can we conclude? So if A is a set of, if you look at the same set A here, all the edges leaving A in the original graph must be at capacity. Yeah? And all the edges which are coming into that set must have 0 flow. Agreed? Okay? This set A I am looking at in the original graph. Okay? In the original graph I claim all the edges leaving the set A must be at full capacity, all the edges coming in must have zero flow. Right? So what does it mean, what is the value of the flow then in that case? The value of the flow is basically the amount leaving the set A minus the, remember A contains S, right? I claim that the value of the flow is the leaving set A minus coming into A. But coming into A is zero because all the edges coming into A have zero flow. How much is leaving? The capacity of the edges leaving, right? So what do we know then? We know that the value of the flow is exactly equal to the capacity of this cut. Yeah? Okay. So that must be an optimum flow, right? Because if I found you a cut such that the value of the flow is equal to the capacity of the cut, it must be the right cut. I mean, it must be the right flow because you can't send any more flow than that. Okay? But as a consequence, what do we get? I didn't assume anything other than it's a flow where I couldn't send anything in the residual network, right? So it must be a maximum flow and the value of the flow is equal to a minimum cut. Right? Is that clear? That to convince you that, what is it saying? If the F is, if I have a flow such that there is no path in the residual network from S to T, it means that F is maximum and the value of the flow is equal to a minimum cut capacity. Okay?
Here the cut is only the edges from A to B.
A to B, yes, that's a,
You don't need to care about the B to
no, yeah, that's not part of the definition of a cut. The cut is, right? Okay, the capacity of a cut of a set, when you think of it as a vertex set, is only the edges leaving, right? I mean, right? Okay, because if I remove all these edges, clearly I can't send any more flow than that, right? There is no way to reach S, cannot reach T, right? Because this is a different proof which says that if you cannot find a path in the residual network, that means your flow is equal to the capacity of this particular cut. Okay? All right? So that's another proof that the algorithm terminates with the maximum flow. Okay? And as a consequence you get minimum cut. Okay? So this is a important theorem, and the picture is worth all the text. I don't want to go through the text anymore. Okay? If you want to see the formal proof a bit more mathematically, you can look at it. Okay? All right? Any other questions on it? The idea makes sense? Yeah, you're convinced? Okay, you have to be a little careful because you're saying we start with this network, we're looking at the same set of vertices but in the original graph. That's what is important. The fact that we cannot reach S to T in GF and then we're looking at what is happening in the original network. So you have to be a little careful. Yeah? Okay, you have to compare these two sets in the different graphs. Okay, and understand what it says. Okay? Okay, alright. So the flow returned by the algorithm is a maximum flow because we found a minimum cut. So if you have integer capacities, then the flow will give you a maximum flow and you'll get the minimum cut. And it's important that we use integer flows. Okay. Now you can ask, what happens if you don't have integer flows? Integer capacities. Now you can the flow same argument you can make it work if the capacities are rational. Okay. Now you can say, what if the numbers are irrational? Now you have to think a little bit. What does it mean that the numbers are irrational? First, the silly answer would be, it doesn't make sense because you can never represent the irrational number exactly in the computer anyway, so why do you care? Right? I mean, that's a valid answer from a computational point of view. But mathematically, you can ask the question, I still want to know whether the maximum flow, it is well defined. Mathematically, F is, you can say, yeah, I can work with real numbers. Is it true that the Maxflow mincut theorem holds even with irrational numbers, right, or just real numbers, right? And it's true, but then for that it is not very hard because the graph is finite. You can approach it in the limit and prove by a compactness argument. Okay, so Maxflow mincut theorem is true even for real numbers, even though it doesn't make sense from a computational point of view. Okay, but the right way to prove it is you have to do this analysis and you can prove it. But sometimes it's important in mathematics to see this, right? But so as I said, it's a very important property which we'll exploit many times, that if the capacities are integers, we are, as a byproduct of this algorithm, we are proving that there exists a maximum flow which is integer valued. Okay, it's very important consequence. Okay, we'll see why that is important. Okay, so we get this things. So here is a nice question. So we have an algorithm to find max flow, right? Yeah? How do you find the min cut from that algorithm? So they're equal, numbers are equal, right? If I want to know what is the capacity of the minimum cut, I just compute the max flow and I'll give you the number, right? Because the theorem says that max flow is equal to min cut value, right? But I actually want to find a min cut of minimum capacity.
Find the number of mutually destroying paths.
No, but the cut is a partition, no?
Yeah, but by the inverse theorem, the number of destroying paths is
Okay, but I have capacities here. I mean, that's true if the capacitor integer, right? But I can have a fat pipe, no? I can have 100 units, but my flow is not 1 unit, right? Menger's theorem holds only when a capacitors are all 1 unit. It's true, you can split the edges and stuff. Okay, if you find a lot of paths, disjoint paths, so how do you give me a cut though? You still have to give me a cut, no? Okay, the proof has to give you the cut. Yeah, exactly, right? So here is the proof is going to give you the algorithm. What did we do? How did we prove the Maxwell min-cut theorem? We said we have a flow. How do we check? Okay, let me ask you a simpler question. If I give you a flow, how do you know it's a maximum flow or not? If you want to know, I give you a flow, right, and say, is this a maximum flow? I don't want you to solve the maximum flow problem. I just want you to check, is this a maximum flow? Right? You create the residual network and check whether you can increase the flow, right? That is there a path from S to T, right? If there is, then you know it's not a maximum flow, right? Because you can increase the flow, okay? If it is not, you know that it is actually a maximum flow, right? But how did we prove it to you in this? We said if it is not if it is a maximum flow, that means that we cannot increase the flow in the residual network. How did we do the proof? We said we find the reachable set from S, and if it doesn't include T, then we get stuck, right? And we proved that in fact that set is actually a minimum cut, right? Okay, so that's it. The algorithm is take F, first you can check whether it is a maximum flow by checking, compute the residual network. Find all the nodes that S can reach in that. If it includes T, you know it's not a maximum flow, right? Because you can find a path to T. If it doesn't include T, that means that, okay, I got stuck with this set that I can reach, and that set must be a minimum cut from the proof. Yes? Agreed? So you can do two things in one shot. Given a flow, you can check whether it's a maximum flow in linear time, right? Because all we do is compute the residual network and do reachability. Okay? Once I give you a flow, you can check whether it is a maximum flow in linear time, and you can find a minimum cut from a maximum flow in linear time. Right? All you're doing is reachability. Okay? Okay? So very simple, very nice. Okay? Okay. All right. Let's see. Okay, I guess we. Okay, so now we at least know that this algorithm will converge, will terminate in integers and will stop. But the algorithm's running time, what we proved is that it is m times c, right? It may take a long time to terminate, and for example, in that simple graph, if c was 200,000, it's very easy to write 200,000, right? It's a very short description. In digits, it's 200,000, but how many iterations will it take? If you're not careful, it can take 200,000 iterations. So it's not a polynomial time algorithm, right? Why? Because the running time is depending on the unary representation, not on the binary representation. If it is log of c, then that will be polynomial time, but it's c, so it's not a polynomial time algorithm, right? Is that clear? Right? Because it's a very slow algorithm in some ways, right? If the numbers are large, if the numbers are not large, then it's okay, right? Okay. So we want to avoid this kind of behavior, right? So so the question is, is there a polynomial time algorithm for maximum flow, right? And also we want to know, is this the only way to find, this is a very simple algorithm, right? What do? We have a flow. If you look at the residual graph, find a path, augment it, add it, and it's a very simple algorithm. This is called an augmenting path algorithm. Okay, why is it called an augmenting path algorithm? Because in each step you're finding a path to augment the flow in, right? You don't have to find one path. Maybe you can do something clever. In fact, fast algorithms use some very clever ideas. So, but this is a simple algorithm, so it would be nice if you can prove that there is some basic variant of this which would give a nice fast algorithm, right? So it's basically saying, can you choose the paths cleverly so that you get faster running time? Okay? Which path should you choose, right? What would you choose, right, as a heuristic?
The maximum, the path that maximizes
Yeah, so I mean, so that makes sense, right? Why, if you look at this example, why did we get bad behavior? Because we chose this path which had very little flow on it, right? 1 unit, while we had another path where we could have chosen C units, right? So obviously, one simple heuristic is find always the path where you can send as much flow as you can, right? Greedily. Okay? There could be many paths in the graph, right? And find a path where you can send a lot of flow. Okay? That's one thing. That's called the fat path heuristic. Okay? Because you find the fat. What is the definition of the path? It's called the bottleneck capacity. The other thing is, surprisingly, you find the shortest path. Shortest in just the number of hops. So you see in this example, why did we get bad behavior? Because when there was a two-length path, we chose this long path, right? Somehow that's very bad. Okay. Okay, now you say, I can change the example and make this bad behavior happen even with the short path. But it requires some insight, but short paths are good, long paths are bad. Okay? Okay? So, in fact, if you use BFS, how will you find a path, right? You may say, I have code for BFS, and you just use it in the residual network, right? Maybe you use BFS. In fact, if you use BFS, you get very lucky. If you use DFS, you may get bad luck, right? You don't know, right? But if you just say, I want to find some path, right? And you use BFS, you'll actually get very good performance, even though you don't know why it's working well, okay? If you use DFS, you'll get bad performance, okay? You may get a bad performance. Okay, so I'm going to stop here, but I want to stop with the following question for you, right? Because that's a heuristic, right? I have a graph and I have numbers on it. Capacities. I know S can reach T. Okay. I want to find the path which has a maximum bottleneck capacity. Okay. So what does it mean? That means among all paths from S to T, find the path on which I can send the maximum flow. Okay. What is it? How much can I send on a path? The minimum capacity, right? Along the path. So that's called the bottleneck of the path. Okay. Because that's where I can't send any more flow than the minimum capacity, right? So I want to find a path which has the maximum of those minimums. Does it make sense? What I'm saying? Okay, in this, let me give an example. I don't have an example here. Let me go back to the a nice, little bit bigger graph. Okay, so take this graph, right, for simplicity. Don't worry about the flow number, just look at the second numbers, 25, 15, 20, 10, 15, right? That's say initially 0 flow. If I send flow along this path, how much can I send? 5. Okay, but if I send along this, I can send 10, right? So I want to find this. Okay, among all paths, I want to find the one which has the maximum bottleneck capacity. Can you find such a path? How can you find such a path? Efficiently.
The maximum edge of the minimum edge.
No, how do you find such a path efficiently? So I give you just this graph and say, give me a path with which maximizes the bottleneck capacity. All paths? That's not very good. We are in the algorithms class. You never enumerate. Okay. Yeah.
You can do BFS with upper bounds being the edges as we compute,
Okay. Okay. Your algorithms, right? Don't try to cook up new algorithms. Okay, because that's always tricky to prove, even if you're correct, right? So you want to think about it using existing algorithms, right? Okay. And many people don't use binary search, even though it's a very important technique. Okay. So when you want to do optimization, you should always think about decision also. Okay. So here is an easier question for you. I want to know, is the bottleneck capacity at least 100? Can you solve that more easily? What does it mean? What does it mean that is the bottleneck capacity at least 100? It means that is there a path from S to T where every edge has capacity at least 100? Is that easy?
Just remove all the paths.
Yeah, remove all the edges which are not below 100 because I don't want them, and then check reachability. Okay. Now once you have that, you can do binary search, right? Okay, that's one idea, right? Another way of, you can do many clever things, right? Okay. Okay, another way of looking at it is you can modify Dijkstra's algorithm. Okay. Okay, when you think about why modification of Dijkstra's algorithm works, you can do it a first principles proof, why that works, okay? But that's a little tricky, okay? I mean, you can prove it, it's not hard. But one way of thinking about why Dijkstra's algorithm can be modified is the following. Suppose, what does Dijkstra's algorithm do, right? It finds the shortest path where the length of the path is sum of the lengths of the edges, right? Okay, what if I want you to find the shortest path where I square the lengths of the edges? Does it find it? It will, right? Because it is you can work on you just square the edges, lengths, and then run Dijkstra's algorithm. Okay. Now, will it work with cubes? Yes, because you just cube the edges and just run, right? Okay. What the bottleneck is that you basically make it infinity. Okay. If you want to find, it's the same as finding the length of the path where the measure is the smallest guy. Okay. So you can think of finding the path with the smallest bottleneck, maximum bottleneck capacity as L infinity norm of the edge lengths on the path. Okay. So that's one way of thinking about why Dijkstra's algorithm can be modified to give you that. Okay, so I'm not saying it very clearly, but you can do that also. Okay, so those are two ways of doing it, which are more systematic rather than cooking up new algorithms and then wondering whether it's correct or not. Okay, try always to use existing algorithms as much as possible, because then you don't have to worry about correctness, right? If you see it at the high level, then the proof is easier for you, right? All right, and binary search is your friend. Okay, when you want to optimize, you first have to think, if I'm trying to solve optimization, I should at least be able to solve decision. Okay? If you can't solve decision, it's more likely that you will not be able to optimize. Okay? Right? So you should first think, if I can't do optimize, can I do decision? Okay? That helps. Right? Okay? Alright, we'll see that more next.